Hi everyone. Warm greetings after 24 hours of intensive contest, and I'm glad to see so many people survived these 24 hours and they're still with us. So basically, for today we have a short program with just 2 sessions. On the first one, we will have an introduction to deep learning, and later on we will have also a part where we'll discuss best solutions for the contest. So without further ado, I would like to introduce our first speaker, Artur Petrosyan, who basically will give you an introduction to deep learning. Artur, the stage is yours. Thanks for joining.
Thank you very much. Do you see my screen?
Yep.
Yeah, okay. So again, hello everybody. My name is Petrosyan Artur, and today I will talk about deep learning introduction. Previously, you already learned some classical ML algorithms such as gradient boosting. You also probably know about linear regression, about logistic regression, and now we move on to more complex algorithms. We discuss its applications, some basic properties, and finally we implement a convolutional neural network in Pytorch for simple image classification problem. So, but first of all, let's start with a general idea why we need deep learning. As you know, the classic machine learning algorithms requires features. I mean, if you want to solve some insomnia problem, like in your competition, you need some things, some features about the particular man or woman, and make your algorithm works on these features. But we are not always have features to use it. For example, if you have an image, you don't have features. You can do it manually, some handcrafted features, I don't know, for tracking some patterns on your image. But with classic ML, you cannot just give an image to your algorithm and make some and solve some classification problem. For example, woman it is or a man, and deep learning methods allow to do this. So let's also think about where deep learning is used. Basically, nowadays it's used almost everywhere when you need, and every time you need to solve some complex problems. For example, when you use Google to search something, when you translate language, you basically use deep learning for it. Deep learning models understand what exactly you're saying and find some relevant documents if you search, for example, and if you translate, it somehow understands general context and correctly translate your text. If we will talk about some more complex situations like self-driving cars or reinforcement learning, deep learning is also used for these purposes. But it requires a lot of skills, and it requires very simple, very hard, very deep and complex architectures to do it. So, but for now, let's take a look at some demonstrations of what deep learning can. First link is just you can type some text. For example, machine learning. Machine learning is, and the deep learning will continue the text which you already typed. Sometimes it's not good. Okay. But sometimes it's good. Let's take a look at the other example. Every time it's some kind of random here, but you can see it generates some text or some cool text. I can say. Well, in this example, we can see that machine learning can understand what you're talking. Not machine learning, deep learning can understand what are you talking about, and somehow write another part of your text. And if you will go to the second link, you will get to. I'm sorry, I'm pre-generated it. This website can transform, can generate an image over your description. So you can type some description here. For example, I've typed dog, and it will take some time to generate an image. So you can get something like this. I think that it's not state-of-the-art solutions, but still, its neural network can generate some cool images just when you pass in a description. It's very cool, I suppose. So we now discuss some applications of deep learning and see some websites with examples. It's not the best what now science have, but it's what you can see in the public. What can you use? Just enter in the website and using it. So let's move on to other slides. Okay, we discussed some applications. We for now know that it is useful in many fields, but let's begin with something simple. Yes, these applications, as I said, requires very deep neural networks and very special architectures for every of these tasks. But let's begin with very simple architecture called fully connected neural network. Let's discuss it. We have some input layer which consists of 3 neurons. It's white circles. And then we take these 3 neurons and linearly, I mean with some coefficients, we transform it to the one hidden neuron. Yeah. Again, we take, for example, first neuron, multiply it by some weights. We take the weight. We take the second neuron, multiply it by some weight, and do exactly the same with the third one, and take and get there some intermediate is a hidden neuron. We do exactly the same with all 4 hidden neurons, and finally we do the same with the next layer. We take this hidden layer neurons and linearly transform it to the some output layer. For example, you can predict, I don't know, insomnia. For example, you take 3 features and somehow linearly it firstly to the hidden layer, and then you predict your target variable, for example. But you may ask me, so what is the difference? Linear regression just take some input, some 3 input, and get you, for example, you train it to predict some target variable. And now you can say, you tell me that I need to take that input layer, somehow transform it to the 4 neurons, and then only predict some target variable. Why it's better? The key point here is we use, I don't say it before, but we use in hidden layer, we use non-linearities. Non-linearities are different. Non-linearities, for example, is also called the activation functions. For example, you can take the relu activation function, which are 0 if x is less than 0, and x if x more than 0. And if you apply this nonlinear activation, you can solve non-linear problem. Again, this is a very important idea. If we use such neural network architecture, and in hidden layer we also add an activation function, for example, relu. Basically, it's not you can add almost any non-linearity, you will now able to solve non-linear problem. Yep, you make some non-linear predictions for now if you just add the activation function after the hidden layer. Let's look at some examples. Let's also here go to the link, and probably now you will understand what I'm saying about. Let's look some problem. For example, this one. We have two classes, yes, orange and blue, and we have some input features. Yeah, we pass it for at the beginning to 4 neurons, and then to apply the TANH activation, and then we pass it through 2 neurons, apply TANH activation, and then finally we make some prediction. Let's train this simple neural network, and you can see that it's easily or not so easily, but it learns some nonlinear dependency. Yeah, it's learned this dependency. If we increase the number of neurons or number of features, it's probably will be easier to do even. Yeah, or maybe not. So okay, that's not perfect, but still it's very good, and it's correct classification here for all examples, as I can see. So, but let's move to the more complex problem. If we take, for example, this data set, it's very nonlinear and complex problem. But let's add some features, all available here basically, and add more neurons to make our neural network more powerful. And as you can see, it's not so easy to solve this task, but still you can see that we need to wait some time, and you can see that it's better, it's becoming better and better. And for now, it's not perfect, but it's still a very good approximation for such complex function. Yeah, it's solve obviously nonlinear problem, and it solved it not perfectly, but very good. If you somehow tune params of such neural network or wait longer, you probably make better predictions. Let's take a look. Let's for example, I don't know, maybe we need to reduce the neurons count for better for faster convergence. Let's see what we get if we start with other amount of neurons. So this time is not so good as the previous one. Maybe we need more neurons to solve this problem. However, as you can see, our neural network tries to classify, but not this time. Okay, let's take more neurons, maybe even more layers. But there's a problem. It can take some time to classify it. Maybe the general idea here is that you can approximate very no, as you can see, for now it's almost perfectly approximate our data, and the main idea, the key idea here is that even such simple neural networks will solve the complex dependencies. And let's go back to the slides. Okay, we now know that fully connected neural networks with I don't know 3-4 layers can solve this pretty hard task. I mean, not linear task. But how train? Firstly, you need to know what is gradient descent, but I suppose many of you know. But if you don't know, it just recalculate some gradient and move to the anti-gradient to reach some global and or local optima. And how the full pipeline look like? we take, for example, an image, somehow passed it through our neural network. For now, it doesn't matter. I explain it later. And for example, your neural network take this image and say to you, okay, it's 99% that is dog. And for now, you can calculate some loss. And then you do the backward pass and calculate all the gradients. So you try to somehow improve your network. You calculate the gradients and make the step towards this gradient. And each time you do it, your neural network become better and better. And finally, your neural network will classify this cat as a cat with 99%, hopefully. So, but okay, you may think that, okay, I tell you that such simple neural network can solve pretty complex problems. But okay, why we need other architectures, or why we need other lessons to learn deep learning if we can take basically any data, pass it through a simple fully connected neural network and get a result? And there exists a universal approximation theorem that, loosely speaking, says that such simple neural network can approximate any continuous function. So why we need other architectures? The problem here is that optimization problem, when you use a large fully connected, for solving really complex problem, you need to very large fully connected neural network to do it. And if you have very large fully connected network, you face with the optimization, very hard optimization problem. And basically, you need firstly a lot of data, you need a lot of resources, and still optimization problem is very hard. You just can't solve it directly with fully connected neural network, and that is problem. And here is why the scientists investigate some new architectures which get the better results from reducing complexity of optimization surface. But we will talk about it later. So for now, as you can see, as you know probably already, we will today we will do our neural network with Pytorch. There is other frameworks such as TensorFlow, but for today we will use Pytorch to implement our neural network. Let's move to the code. And you can get the notebook from our repository, DL intro, a Python notebook. I recommend you to use curl for this notebook if you do it with me. But I personally do it with my own notebook because I need a strong GPU for some tasks here, and it will be better for me to do it on my local machine. Okay, let's start our introduction to Pytorch. Quick introduction, mini presentation we already done. So let's move to Pytorch. If you need to install something, install it please with pip. Just uncomment these comments. Install. We need to Pytorch, NumPy, sklearn, tqdm, and matplotlib for now for today. Okay, let's start with NumPy. Every one of you probably familiar with NumPy, but let's just a little bit remember it. Let's import it and do some basic operations, such as we create some random matrix. Then we also could take a shape of it. Yeah, we can, for example, add a 5 to our matrix. We need for now, it's very simple operations. I'll tell you why. Then we need to, when we want to calculate the matrix product, so take the column mean, change the shape, probably you know all of that. That's some simple operations that every one of you probably can do. Well, for now, I need to show you that Tensor or that Pytorch is really look like an NumPy when it comes with basic operations. So let's import a torch. Yeah, let's randomize. Let's get some. Now it's a tensor. Be careful that before when we use NumPy, we use array class, NumPy array class, and when we use the torch, we use a tensor. Sorry, I need to read the chat. Could you zoom out the screen? Okay, sorry. Small. Okay, thank you very much for your comments. So just go and view options. Yes, view motion. I can. Okay, probably like I don't need toolbar and header. Okay, that's should be fine. Thanks a lot for your comments. As I said, we import a torch. We then randomize some tensor. Be careful, now it's a tensor. We cannot work in exactly the same as a NumPy, but we can do the same. Not exactly, but it's where it look like NumPy. You can take a shape of it. You can add 5. You can apply matrix multiplication here, and you can get a column mean, for example, if you want it. If you want it, you can reshape it and take the tensor with other shape. Why we need it? Why we need to use torch? I'll tell you later, a little bit later. But for now, takeaway message that you can use torch for very basic operation, just like an NumPy, with minor differences. So let's move on to the next thing. Our task for now is to write the linear regression problem with Pytorch. When we write linear regression problem, we can move on to the more complex problem, to the real neural network. But for now, let's just write a linear regression with Pytorch, with a gradient descent optimization. So for it, we will use a Boston dataset. We take the target from this dataset, and we take some feature of this dataset. It doesn't matter what the feature and what the target for now. If you want a description, you can get it from boston.desker. And get description of the set, but for now it really doesn't matter what these features is about. We just assume that we have just one feature and we have just one target, and we have a regression problem. We need to recover the target from this feature. Simple regression problem. That's how we can do it. Firstly, what we need to do, we need to create our tensors with weights. For now, our tensors will be just a scalar. Yeah, we randomize our weight for our single feature, the only feature that we have for this example. And the important thing here, we also created with requires grad param. What it means? Requires grad tells to the Pytorch that it need to keep and calculate the gradients for this particular tensor. And previously I said, why we need to even use torch if we have an NumPy? The main difference here is that torch can calculate the gradients over your operations. You are doing some stuff, you're doing some multiplication, summation, it doesn't matter, it keeps the gradient if you tell Pytorch to keep the gradients. And this is a key difference. This is why we use Pytorch for deep learning and not an NumPy, one of the reasons. Okay, we created weights, we created a bias. Now we need to convert our data set to tensor. Also, we take the only feature. We scale it with the divide by max and create a tensor. We're doing the same, but without dividing for our target variable. And then you might notice that, okay, the difference is a question from chat, a difference from the TensorFlow and Pytorch. We can discuss it later, please. It's not one word. It's not a very simple difference. That's for now. Let's begin. Let's continue our ideas that we for now do not have a gradients because we just created the tensors and it's just not have gradients for now. For make some gradients, we need some loss function and so on and so forth. So let's do some predictions with our regression. We need to take our weights. Yes, we need to multiply it by x, and then add b, and that's how we get the predictions. Yeah, just like in linear regression with only one feature. One feature multiplied by the weights and add bias. Very simple. Then, as in linear regression, we need to calculate mean squared error loss. How we can do it? We get the difference between the y pred and y, and we square it, and we take the mean squared error. Very simple. Then we need to calculate a gradient. So we don't need to calculate it manually with math. We just can call a backward method, and it automatically calculates gradients for you for all what you've done before. So let's see. That's for now. The gradients is calculated. When we just created, there is no gradients with your weights and biases in your weights and biases, but for now we have gradients. So if you have gradients, we can optimize our regression model. Yes, let's move to the optimization loop. So we at every iteration we make a predictions. Yeah, with our weights and biases, with our weight and bias. Then we calculate the mean squared error loss. Then we call the backward method, and then we do the gradient optimization step. We do it with some learning rate, of course, and finally we need to. Torch is by default is remembering previous gradients, so we need to drop it. We need to call the zero methods, and on every iteration we calculate loss. We calculate loss, then we calculate gradients, then we do optimization step, and then we forget the gradients. Very simple. So let's look how it optimize it. Yeah, you can see that we at initial time we have some random variables or random values of W and beta and B bias. And for now, we can see that it's somehow look like that it's fitted over our data. We can also, for example, make more steps to make it more closer to the some optimal solution. Here, the takeaway message: what we've done now. We've we've made a linear regression with a simple low-level Pytorch. We calculate loss, take gradients, and make a solving regression optimization problem. But you can say, okay, we're here for learning some about neural networks. You just and you telling us about linear regression optimization. So let's move on, and pretty soon we will create our first neural network. But firstly, we need to do, before creating our neural network, you need to somehow deal with your data. In this example above, you just pass all your data in every iteration. Yeah, no, you calculate the loss function over all your data that you have. But what if your data, I don't know, it's about 100 gigabytes. You can't just apply your neural network on this whole data every single iteration. So you need to implement the batching. What is batch? Batch is just a random some sample of your data set. For example, if you have in your data set, I don't know, 1,000 photographs, you can just take a random 10 or random 100 photographs and train your neural network on these 10 images for one iteration. And then another iteration, you take other 10 random images. And what these 10 images is called batch. And you need to implement it somehow, this batching pipeline. So Pytorch is already have something for it. It have two classes. First class is a Torch Chills data set, and the second class is Torch Chills data loader. The first class just storing your data, and you can access any object of this data set by indexes. So here we create a simple example. We inherit from Torch Chills data set. We initialize our data set. We just pass X and Y to this class and save it in memory. And then we implement two methods. First is len. We saying how the length of your data set. And the second method is get item. Get item, you can get item by index. It's as simple as it can be. Just we create, for now it's random X and Y, yeah, and path it into the random data set class and create our data set. We can get any item of it, but why we need it? It's a simple operation. We can do it without this class. It needed because then we need to pass this object, our data set, to the data loader, and data loader creates a batches for you. So again, you pass your data into some random data set class, and then you pushed it to the data loader, and data loader create batches. So look, let's look how it works. We created a data loader which takes as an input our data set, and then we also add batch size 4 here as an argument, and now we can iterate over it. For example, let's take a look at the first batch, how it looked like. It looked like a tensor with four objects in it. Yeah, why 4? Because batch size equals 4. If we take batch size equal 10, we will get 10 objects. I printed a particular batch. It's just a 10 random, maybe not random for now, because we need to additionally add the shuffle argument, but it doesn't matter. It's for now you can think that it's just 10 random objects for your data set, and you can use this subsample to make one step for your neural network. Yeah. So finally, takeaway message here that we implemented batching with data loader and the dataset class of Pytorch, and now everything is ready except the neural network for training neural network and deploy it. So the first thing we need to do, we need to create our neural network. How we can do it? It's the main thing for today's lesson. How to create simple model, fully connected, for example. Let's begin with fully connected. There is a different ways to do it. Let's discuss about second one because it's quite easy. First one, it's also easy, but the second, okay, we can describe the first one if you want. First of all, we create an empty model. with an unsequential, and then we just add a model. We append the layers to our neural network. For example, first we add a linear layer. Linear layer is just one thing. There's a first, it's weight between input layer and hidden layer here. Yeah, we just add linear layer. Then, as you already know, we need to add an activation function. For example, here we add a ReLU activation, and finally we add some other linear layer to make our predictions. Let's see how it works. We now created a simple neural network model, and we can apply it. We can take our batch, which we get in a previous step, and pass it through our neural network. You can see that that's how we can do predictions. Yeah. Again, very important thing to understand that. Oh, sorry, I need to. No. Sorry, I forget how to add a toolbar. So how to add a new section. We can see this batch. It's size of 10 objects and 5 features. Be careful here. It's a little bit difficult. Then we apply a linear transformation, which take 5 features and produce some other hidden features. Then we apply activation. Then we transform these 10 hidden features after activation and get the result. Result is just a one neuron, is one target variable, for example. But it can be more. If you, for example, solve, I don't know, 2 problems simultaneously. But for now, it just one-dimensional array. It's your predictions. Finally, let's apply it to some real problem. For now, we will use a MNIST dataset, and Torch is already has here. As you remember, we implement for some random dataset. We implement a custom class and use it in data loaders. But for MNIST, Pytorch is already created a class, and you can use it. So we use Torch Vision dataset MNIST, and that's our test train dataset. And the same thing, you pass train equals false, and you get the validation dataset. And you get all the dataset and pass it to the data loaders. Yeah, you can see that we take the MNIST train and pass it to the data loader and get train data loader. I can think that I can tell that it's just like an iterator over your data, as you already know. We need to shuffle it, and batch size equals 4 for now. So let's do it. If you do it with me, it probably takes some time to download it, but it's about 10 megabytes as far as I remember. So it should be very fast. So let's see what we have here. We have digits. This we have 5 and 0, and we need to classify it. We need to classify digits. So how we can do it? Firstly, in a very simple setting, we can just flatten all our pixels. Yeah, you understand that each pixel is a digit. No, it's not a digit. It's a number, some number. Yeah, and you can use it as a feature. Just convert 28 to 28 image into some 784 vector of features, and then you can apply a fully connected neural network to it. You can use linear layer is input features in 784. Then you convert it to the vector of size 128, Then you apply nonlinear transform, yeah, and finally you you transform this 128 vector with some hidden features, which neural network will learn, and to the 10 classes, 10 digits. So we also create an optimizer. We need to somehow optimize it. In our previous example, we do it manually. I mean, we just make a step by our hands. But with Pytorch, you of course can do it automatically. You can create an optimizer. You can pass the model parameters in it, and it just will optimize for you. Do the all job for you. So let's create it, and let's finally we will discuss the training loop, how it look like. Let's take the first part. Here we iterate over our train data loader. It's our all training data. We get some batch of data, X train and Y train. Its size of 4 images in each of them. No, I mean that X train consists of 4 images, and Y train it's just labels, 4 labels for 4 images of X train. Then we take our X train, we apply a model over it, we take a predictions. Yeah. Then we calculate loss with cross entropy, and then we calculate the gradients. After we calculate the gradients, we do a step. Now it's done automatically because we used Torch optimizers. And now we, as in previous example, we need to zero the gradients. Yeah, to drop previous gradients. Okay, that is how it works. Also, you can see the Pytorch here. Pytorch, it's just one. It's when you go through all your data set once. Yes, it's called the Pytorch. And for example, this is one Pytorch, and let's start our training. Yeah. Also, you can see below. It's a validation loop. We do exactly the same. Besides, we don't do the step, and we don't calculate the gradients here. We don't need it for our validation data set. We just need see the quality of our classification when we use validation data set. And as you can see, it's very fast learns to the accuracy of 96%, which are pretty large accuracy. However, it's just simple MNIST data set, and even if you apply, I don't know, the gradient boosting algorithms, it will be even more quality for it. Let's move to the other theme. Let's move to the convolutional neural networks. Okay, we now for now applied a simple fully connected neural network and train it on MNIST dataset and get 96% accuracy. So now, if we will try it on more complex dataset, we will do it today, a little bit later. You will see that fully connected neural network is not doing very well. So how to improve it? We need to switch to convolutional neural networks. Let's discuss about how it works. Firstly, we need to understand what is simple convolution. Convolution is just an operation. Let's take a look at the example. It will be easier to explain on example. So we just use some kernel, for example, 3x3 size. It's just a weight, which you can learn, by the way. But for now, it's just some weights, and you slide over your image with this kernel and get convoluted image. How you get it? Let's take a look at the orange square. we apply the kernel to this orange square. I mean, we multiply 2 by 1, 5 by 2, 4 by 1, and another. We doing this multiplication and then sum all of it up and get 198. Yeah, you can see the simple calculations here, and you slide over all its image like that, and finally you get convoluted image. But why we need it? Basically, the convolution, it's an operation which can extract some meaningful things from the image. For example, this kernel, it just extract some edges, vertical edges from the image, and if you extract these features, for example, edges, you can use it then in your other part of your neural network. Sorry, I need to answer some questions here. CNN provide very good accuracy. It's great. Yeah, it's in comparison with fully connected neural network, it's a lot of better. How the kernel matrix is selected? Kernel matrix is learned due to backpropagation, as we learned in fully connected neural network. I'll tell about it a little bit later. So for now, we can see that these kernels is extract some features, some things about the image, and we need to also discuss some other operations which called the max pooling. Max pooling is just a way for make your image more smaller. Usually images is pretty large, and when you apply some kernel, some filters, you don't need to the full image. You just need to reduce its size, and you apply a mean pooling when you mean all the pixels from some square, or the max pooling. Let's look at the example. We have some red square size 2 by 2, and we take the maximum from it. It's a 6, and in our next reduced size image, we write a 6 here, and we do it this with all the squares of size 2 by 2 in the image, and finally we get a reduced image, and finally you can create an architecture. It's look like this. You have an input, some input. You apply a convolution. At the initial time, just initial, just random weights, as previously in our fully connected neural network, just random filter. Then you apply the ReLU activation to make it non-linear. Then we apply pooling to extract some meaningful features and reduce the size of our image. And then we do the same thing twice or I don't know, 100 times. Depends on how much resources do you have. And finally, we push it to the fully connected neural networks and get a result as a classification. It's look like that. Again, we take a car image as an input, for example. Then we apply convolution. Then we apply ReLU, and so on and so forth. And finally, we pass it to the fully connected layer and get results. Yeah. Why it's better than fully connected neural network? Because it's use very little amount of weights, and it slides over your image and find some pattern or apply some transform over image. And it's optimizationally it's pretty easier than pass all of your image to the fully connected neural network. And it's provide better results, significantly better results, as you can see later today. It's provided significantly better results. than a fully connected neural network. So that's all about presentation. Let's move to the code and do exactly what I said. Let's wrap our previous code into the method. Yeah, we here have a code that's do training of some model. Let's do the same, but wrap it with a method, some function. Yeah, it takes a model as an input. We provide some optimizer. We create a train data load. We pass train data loader, while data loader, and everything is done as before. We just train our neural network. But now let's look at some more complex example. Let's take a CFAR data set. We also, as a previous mini data set, we take this dataset class from Torch Vision. Yeah, Torch Vision dataset CFAR, and create a train and val data loader. So let's look. Let's take a look how it look like. It's something like that. The first is a frog. The second is a truck. No, you may see that's images with some classes, and we need to classify it. It's more complex task. Significantly more complex task than just classifying the digits as we do previously on NIST. And we also need to create some model here. Firstly, we need to create this model. Our image now is 32 by 32 size. And it also has 3 channels RGB. Yes, red, blue, green. We can, as previously, we can flatten it just in vector of features and pass through a simple fully connected neural network. Let's do it and see the results. Here it takes longer to train. But you can, I'm do it before, and for this simple architecture, you get the accuracy about 33%. Now let's take while it's training, we will not wait before we just switch to next architecture, and then we'll see the results after some time. Let's create other fully connected, convolutional neural network. For now, we do not use a flatten as a first step. We applied the convolution operation. For example, here you have an input tensor of size 4 by 128 by, oh, sorry, no, 4 by 3. 3, it's RGB, red, green, blue. And now images of size 32 to 32. And we applied our convolution layer. We applied the ReLU after it and max pooling. After it, we get some filtered images with some patterns probably, and reduce the size by a factor of 3. I mean, if you have image 30 to 30, then you, after applying the max pooling, you get the image of size 10 by 10. Then you do exactly the same to apply. You apply the other convolution operations. At the beginning, I need to say that at the beginning it's random, but due to backpropagation, it will learn optimal weights. You apply the convolution operation, you apply the ReLU, and you apply the max pooling. And finally, you get a little image with already extracted some patterns from your images. And you can see that that here it's the size of it's 128. It's a number of kernels which were applied, and the image is size 2 by 2, very little. We flatten it to the vector, and then we pass it to the fully connected layer, and we learn it, and we learn these weights. this simple convolutional neural network, already if you apply it, you'll get at least 60% of accuracy. Yeah, you can see that our previous fully connected neural network learned for now, and it reaches 35%. If you train longer, you will get, I don't know, at max 40% accuracy. And if you will train, now we will train as a convolutional neural network. Let's stop it. It will not reach significantly more score. And if we train the convolutional neural network, you will get significantly more greater accuracy. And I should mention here that its convolutional neural network is still very simple. If you train it longer, and if you do it larger, then you can get easily you can get more than 80% of accuracy, even more than 90% of accuracy you can get but it's will take a lot of time and a lot of work on architecture, or you need to take some ready one. Okay, we need to wait some time while it's training. And finally, I want at this point to compare it with previous methods like CatBoost classifier. If you will train CatBoost classifier here, you will get accuracy about 57%. It's pretty large. Why it's better than, for example, our previously fully connected neural network? Fully connected neural network is pretty simple, for this version there is no applied any regularization techniques. In contrast, CatBoost initially has some regularization things in it, so it can learn better than super stupid fully connected neural network. But if you, as I said again, by the way, look at the accuracy. It's just one approach, and you'll get significantly better than you get with fully connected neural network. As I said, if you want to apply CatBoost here, it's also here a nice accuracy, but nice in comparison with fully connected neural network. If you train longer, if you train your convolutional neural network, you can get about 60 or 65% from this architecture. If you spend some time to tune it and add some layers, which I don't cover in today's session, you'll easily can get 80%. And if you wait significantly longer and a significantly better architecture, convolutional architecture, you'll even can get more than 90% of accuracy, while simple CatBoost gets only 57% accuracy. So it's convolutional neural networks on images is significantly better than the classic ML algorithms, and then a simple fully connected neural network, which we discussed today. So I'm sure that we need to wait for training. The CatBoost classifier is also trained for some time. You can just believe me. I get these numbers just running this code. I'm not sure we need to wait for this training. You can do it by yourself if you do it with me, or after our bootcamp if you want it. So probably it's all what I want to tell you today. I need to answer some questions. Sorry, I skipped it. Max pool layer and freeze layer diff. I don't think so. I know what is freeze layer. What do you mean by freeze layer? Probably it's not the same. Maybe you mean that sometimes you freeze something, some layer. It's not the same. It's different things. Why ReLU between two convolutions? Because in our neural network, we need to make it non-linear. Yeah, we need to apply activations to get our network to let our network to learn some complex patterns. If you leave it linear, I'm not sure that it's can learn a lot. How I can get started with machine learning? Can you suggest something? Okay. Probably you can start with our bootcamp. But now we talk about deep learning, and for deep learning you can just learn this lesson which we discussed today. Instead, ReLU, we can apply some other non-relative function also. Yes, you can apply a lot of activations. I cannot say that you can apply any nonlinear function because I'm not sure that that it will lead to smooth optimization problem, or not smooth, but it's if you apply some very complex activation function, it probably will not easy to learn some pattern by your neural network. And if you use some predefined, some already known activation functions, yeah, there is a lot of YELU, leaky YELU, I don't know, it's a lot of things. Any of them you can use, and you will get nice results. How many activation functions available to use? It's pretty easy to check. Pytorch activation functions. Oh, activation functions. For example, generally you can see it in Pytorch documentation. Theoretically, it's infinity many, but implementations are for, I don't know how much is that. 30, 50. No, it's already not. It's not activation, but I don't know, many activations are available to use. I'm sure that it will be enough for you to start practice with deep learning. So that's all for today. Thank you very much for all of you. If you have some questions, I can answer it if you write in the chat. If not, thank you. Okay, thank you very much. Goodbye. I'm stop sharing. So that's all.
Thanks a lot, Artur, for a nice presentation. So guys, now we will have a break before the next session. So it will start in half an hour, and we will finally discuss the solution for the contest that we have had. So a break now. So see you in a bit. So let's get back to our sessions. Unfortunately, we have the last session of the whole bootcamp right now, but it probably would be one of the most interesting because it will concern the contest that you've been solving. And I see that the speaker is already here, so I would like to pass the word to Alexey Birshert. Alexey, are you here?
Yeah, hello, everyone. My suggestion is for our invited participants we have invited several participants to tell us about their solutions. My suggestion is that we will first listen to them, and after that, I will present my solution.
Yeah, sounds good.
If they are here, if the people we wrote to are here, let's maybe start with them.
Yeah, we before this part, we actually reached several teams and asked them, one of the leaders on the private leaderboard, and asked them to present. Let me check on the participants list. Here. I see Salil. Salil, are you with us? I will grant you the co-host right.
Hi, am I audible?
Yeah, hi there. We can hear you. Hi.
Would you like me to share my screen? I have made a quick and dirty, like 1 or 2 slides, as you had mentioned.
I mean, the stage is yours. I mean, you can do whatever you like, whatever the format might be preferable to you, either sharing or I don't know. So feel free to improvise in terms of format.
All right. Let me know once my screen is visible.
Yeah, we can see the screen. I think it's perfect. Thanks.
All right. So I'll just give a 5-6 minute brief like an overview of what I made. I didn't do anything very special, but luckily I felt that the last minute ensembling really helped. So I just mentioned all of that. So I'll directly dig into the approach. So if you overall look at it, it's very simple. I started with some feature engineering, and this was an iterative process. I figured out on some I made some interaction features between three categorical variables, which really gave me a boost. Apart from that, as we had very less set of features, and the other thing was that I didn't aggregated features when I was trying, I wasn't able to have any improvement in the local cross validation. So what I basically did is I made 2 set of models, one light GBM and one cat boost, and I created 20-fold 20-fold models for 20-fold models for both the algorithms which I had. And on top of that, after doing a weighted blend of both of them, I even did some seed diversification in terms of my folds. And finally, I ensembled everything and made a final summation. So luckily, it helped me in terms of not falling down in the private leaderboard, because there was a big I would say difference between public set and 33% and the 67% rest. So private LB had 0.53143. I'll just give a brief of what features did I make apart from the ones which were already given in the dataset. So if you see, I made 3 interaction features between stress, sex, stress, doctor, and stress and the Pyrenicus one variable. Apart from that, I also made a difference of the BP variable. I label encoded them because I was using boosting algorithms later on, so it won't be an issue. And if you ask me how did I end up on this, I would say I was using my cross validation of my 20-fold model to act as a I would say a indicator for me to know what's working and what's not. Once I had established a cross validation locally, I realized that it's in sync with the leaderboard, in the sense that any improvement when I made in my local cross validation was also improving the leaderboard. So I then basically iterated over different features. If you look at the model pipeline, it's fairly simple. It's if you see, I did a stratified k-fold. I would say stratified wasn't really necessary because the data was quite balanced, but still I did it. And then I made an LGVM classifier and a CardBoost classifier. And then I was doing a weighted ensemble, which you can see here is 0.6 and 0.4. And finally, I used something which is I saw people use it in Kaggle a lot, which is the log loss clipping, because we had the evaluation metric as log loss, and log loss as a metric penalizes you a lot in case if you are very confident and you are wrong. So when I say very confident, let's say you're predicting your probability as 1, and you're wrong. So the loss will really shoot up. And similarly goes for the other side also. If you think that it's zero and you're very confident and you have given the probability like zero for zero like 100%, and if you're wrong, you will again get penalized. So what people do is that people clip you clip your probabilities between 0.05 to 0.95, so that in case if you're wrong, you do not get penalized a lot. So I did the same, and I also found a bit of slight increase in my local cross validation. So I kept that. Uh, in terms of my local crossword, I had 0.53816, although there was still a gap between the leaderboard and the local one, but still it was in sync in the sense that when this was improving, even the leaderboard score was improving. That's it. That's like a short summary of. In case if anybody wants to connect with me over there, you can feel free to ping me on LinkedIn. Thank you. And I'm open to questions if anybody has any.
Thanks a lot. Actually, I switch on the option of unmuting yourself, so I guess we can have a kind of chat here. So if anyone has questions to Salil or maybe to future speakers afterwards, so please feel free to switch on the microphone and maybe even ask questions orally.
I asked this question in chat and I want to repeat it in the voice. Is there any option that guys from top of leaderboard can send to all the participants their notebooks? Just code, not description of what they did, but their code.
You mean the notebook? Yeah, I can share it across. That's not an issue. Or what I can do is I can put it on my GitHub and send you a link. Or in case if the organizers feel they want to create like a dedicated repo and others also want to contribute, I can push it there as well.
Yeah, Shali, I have a question I heard some of your solutions explanations, but I couldn't get the complete thing. So briefly, can you just repeat if possible, like the main areas that you thought of that could be helpful or give you great results in terms of in the competitive platform?
Okay, so if you ask in general, like based on whatever experience I have of like ML competitions, I would say like it's very important in terms of whenever there is a public-private split, when you are aware that that's going to happen for the final leaderboard calculation, try to ensure that you can have like a cross-validation which is robust enough, or at least you have something to iteratively improve your solution on. So the first thing which I did was just like I did like a 5-fold cross validation just to have something locally to compare from. Because in case if you just keep on trying models without having something like an indicator at your local side to really like at least have some indication that whether adding features is helping or whether removing features is helping. Uh, that would be my like advice. Coming to my solution, what I basically did was I did some feature engineering, and after that I had like two different models, LGPM and cat boost. I had created a 20-fold split of my data, and I was training like with Zod with that, and I was taking an average of all my predictions. And in the last, just before the competition ended, I thought just make it more robust, I added like a seed diversification. So when you're doing your cross like k fold, you can change the random seed. That will basically make your data in your splits different. So that I did, and like I took an average of it in the end. But that's just like I would say very specific to competitions. Like in real world, that's not like a very good way to go ahead with.
Okay, so you use the seed as constant or something like 1, 2, 3 non-zero value.
So 99% of the competition till I was making models, I added constant, but just in the end, just to have a diversification in the end, I changed the seed also, like 2, 3, I think I had 3 different seeds, and then took an average of my predictions after that as well. The whole pipeline remained the same, only the seed changed.
Okay, and when we have a time-bound such competitions, so what kind of feature engineering steps do we need to apply for? Like there are many other feature engineering, but what are the most influencing but generally gives good feature engineering results within a certain time limit?
I would say it's very subjective. Like in case if you know the domain well, then you can even look at like domain level features. Generally, features which people try to make are like people try bins. You can do you can try buckets. You can maybe look at histogram plots of your different categories and your target variable to see like how much is your variable really helping in separation of your target variable. And then you can create new features like I created like a combination of two categorical features, and then again see the histograms to understand that has it made the separation better. You can also try aggregated features, like you can try min max using one category and across a different across the other numeric feature. But I would say there's no golden set rule. It's an hit and trial, and like yeah, that's what I would say. But and yeah, you can use Kaggle kernels. You can read other people's code of different competitions to learn from.
Yeah, and in many of the other questions I saw that generally when the features gives us categorical, then between the one-hot encoding and label encoding, which one should we use? How do you feel? Means that one-hot encoding creates a lot of columns. Can you tell me
Okay,
that?
like in case if you're you just need to be careful in like you can try both, but you need to be careful only in certain conditions where let's say if your categorical variable is an ordinal variable, uh, when it has order in terms of presence, like I say you have a grade feature which is ABCD, in which you know that your A is better than B and B is better than C. In that scenario, you cannot use labeling like you cannot really use label encoding because label encoding just gives it random numbers based on the frequency count. So in that case, you need to use one-hot encoding. Otherwise, your model will not basically know that these are ordinal variables and they have an order. But I would say it's really dependent on your variable. Like, is it an ordinal or is it a nominal variable? And also, as you mentioned, but I would say like even if it has a lot of categories, you can still try one-hot encoding because boosting algorithms still can handle them.
Okay, thank you.
Thanks a lot. And thanks for nice questions too. May I please pass the words also to another team? Like now we will have a team. I think it's called Nuclear Foxes. As I see, Sergey and Evgeny are with us.
Yep, we're
Hello.
here.
Yeah, hi there. So yeah, the stage is yours. I granted you admin rights, so you can like share if you want, or do whatever you like. The stage is yours.
Yep, thank you. Just a sec. I guess this is working now. Okay, so we are the Nuclear Foxes team. We hit the top 7 of the private leaderboard. We had like top 5 when it was in the public. And here's what we've done. We had our data re-preprocessed from the baseline. We didn't fix any nonce in the spot column. We also did the encoding, and we just left the doctors without those changes with one-hot encodings. We have also found that both the UBP and the LBP seem to have some corrupted values, which were like some thousands. And I guess we all understand that both UBP and LBP are like not greater than 300 maybe. And there were also some negative values for them. So we just took the absolute values and somehow trimmed them with some adequate max values. We had like 300. Which was the maximum for UBP and something less for the LBP. We actually found out that UBP and LBP is somehow connected. It's like usually it's LBP plus 50 and you get the UBP. So we tried to replace those inadequate values with some predicted ones, but for some reason it really didn't work. So we just stick to the trimming and taking the absolute ones. We have also looked at the graphs. I'll just skip them through. The main thing here is that both in train and test, they're pretty much the same. And that is why we believe that the private leaderboard might not be so different from the public leaderboard, as the features are distributed so well. The private and public shall be distributed the same way. We also looked at the correlation matrices. Once we had those UBP, LBP fixed, we found good correlation between them, as I've already told. We decided not really to do anything with that. Besides, both UBP and LBP have a pretty good correlation on insomnia, so the idea just to drop some big values might not be an adequate one. We also used TSNE to find some clusters. We hope that we would find some clusters with only false or only true, but as you can see, the clusters don't really help. We have some distributions in all of them, both red and the blue ones. We could somehow use that data probably, if we would say like that this bottom part is mostly false and the top part is mostly true, but we decided not to go with this idea because it was like an overkill for this task, as we believed. So we actually tried a bunch of models. We tried the CatBoost, LightGBM, XGBoost, the TabNet, the simple fully connected layers networks, and just some bagging classifier from scikit-learn. Just why not? And the best result was achieved by us when we took some the boosting models, the XGBoost, the LGBM, and the CatBoost with these coefficients. So we try to tune them too. And these are the ones which were the best for the public scholars leaderboard. One more thing we did is the fine tuning with Aptuna. We tuned the hyperparameters of all of the three models. You can see the importance of the features in the graphs. We have also tuned CatBoost, but actually of all the parameters we tried to tune, it only sticked with the iterations number, so we just put some number in there, and that was okay for us. And that is pretty much it. We believe we could have done better pre-processing on the UBP and LBP, since some of the values are like 106 and 50, and I believe those might be just, they shall be just divided by 100 and we would get a normal number for the UBP or something like that. So we could have done a bit more smarter pre-processing here, but we actually didn't have time. We really screwed with the TabNet, and I believe that this model can do pretty much better. So we shall try training it another one time. And just for some fun, we could also try some convolutional networks. Since we tried the fully connected, we might want to try another architectures. That is pretty much it. We didn't do anything great. We just fixed the hyperparameters and have done a little bit different pre-processing. So any questions?
Thanks a lot, Sergey and Evgeny. If anyone has a question to Nuclear Fox team, please, you may address.
I guess that is it.
Yeah,
We will
I
have
guess so.
the notebook provided at our GitHub. We will give the link in the Telegram chat. So feel free to look into it. We will update it soon, I guess, with some neural networks tryings of ours. So that is it. Thank you.
Thank you guys for participation and for presenting. It's really
Thanks
nice.
for the challenge. It was awesome.
Thanks a lot for kind words. And we also have another another person to present. Rafael, I see that you raising the hand. You can tune on.
Hello, can you hear me? Hello?
Yes, we can hear you.
Okay, I'll share my screen. Well, I didn't do so fancy things like the other guys did. I think their solutions are pretty great. The main thing I looked for was that they were missing some things, but first in the variables, right? I didn't categorize the stress and doctor values because I think they were good like ordinary variables. So I just used cat boost and just rescaled them to work from 0 to 3 and sex to be 0 to 1. So then I decided to infer the missing values on the other columns. So I did grid search to find the best, like good parameters for sport and pernicious 1 and 2, because I think those two variables, pernicious 1 and 2, were like, I think were the most important. So I didn't want to drop any of them. So I tried to use cat boost on the other variables to drop in insomnia and predict based on those, the values for those missing values. So using a grid search, I found these 3 parameters for those models. And then after that, I trained the insomnia model with these parameters. So then for the prediction, I did that, right? I filled the non-values for sport, pernicious 1 and 2 using the other 3 models. And after I filled the missing values, then I did the prediction on the full data for the insomnia with probability. And then I got the result. I think I'm top 5. So, but I tried to do feature selection with logistic regression and cat boost, trying both models, but it didn't improve. Indeed, it raised worse result. So I stayed with the previous approach. So I think maybe I could there is so much to improve, like the other guys did, but this is my solution.
Thanks a lot, Rafael. Maybe anyone has questions this solution or anything else? Any comments?
Yes, Rafael.
Yeah.
Nico Horman from Argentina. Let me get the idea. You used 2 models to fill the NaN values of the columns, and then you train another model to the final prediction, right?
3 models, because sport also had had missing values. Yeah, for example, for sport, I dropped sport and insomnia and used all the remaining columns to train a sport model, then drop the other, but use sport for the other models and then use that data to predict the final model.
All right. Thank you.
Anyone else? Any comments, questions, or anything basically? Okay, in this case, Rafael, one more time, thanks a lot for presenting and for oral participation. It was really nice to hear your solution.
Thank you for the challenge. Thank you everyone for the effort.
Thanks a lot for kind words. And now I guess we are, once we heard the side of participants, I guess it's time to hear the side of Alexey. Alexey, are you with us?
Yeah, I'm here. I'm ready to present my solution. Our solution is rather simple. It is not. It focuses mostly on the cleaning the data, and so I think I'll show you the notebook first, because I think it's the most interesting part. So as you can see, as I noticed first, the test data has about 10% of missing values for sport and both pernicious features. So I had different ideas how to deal with it. The first one was to just fill in the gaps based on some prior knowledge, or with some zeros, some medians, and so on. The second idea was to train a separate model for predicting sport, for predicting pernicious and pernicious 2. And the third idea was to use a classifier that can handle these missing values, and to make some missing values in the training set as well. So the third idea is the best idea. It showed the best results. And so what I'm doing, I'm just, this is the part about missing data. The second part is about fixing upper blood pressure and lower blood pressure and height and weight values. As you can see, most of the values are correct, but they have an enormous amount of outliers, of some incorrect values, of some negative values, and so on. And so the main preprocessing code just takes the data set, concatenates the train and test set, and then after this I just go through most of the upper and lower blood pressure values and fix them one by one. It is not a very clever solution, but it is just a routine. Yeah. After that, after I clean all these upper and lower blood pressure values, I go to height and weight, and I clean these values based on some gender and some normal values. After that, I add some new features, just like body mass index, yeah, and I categorize these features because it showed an enormous, not an enormous, but showed some improvement for the models, for the model training. Also, I add pulse pressure, a difference between upper blood pressure and lower blood pressure, and a category, a binary feature, that is that our pressure is in normal values. So after that, I take the training set and I just randomly erase 10% for the pernicious 1 and pernicious 2 and for sport. After this pre-processing, I take an XGBoost classifier and tune it hyperparameters with an Optuna library. Unfortunately, I have no code for this part because it was a solution. I lost my notebook due to Linux issues, and I only reproduced it, but I didn't have time for filling in all the hyperparameters and all the intervals. But I'm using the cross-validation for 10 folds, and I'm optimizing an XGBoost classifier. Yeah. And after that, I have this model, as you can see on your screen. It has some pretty, it is a pretty huge model with about 1,000 trees. And this submission results in 53,083 on the private score and 54,335 on the public score. And as I suppose on the private score, on the private leaderboard, it should be a top 1 solution, but it is not really very far from current top 1 solution from the participants. And so I could use some tricks as Alil suggested for clipping the predictions, as for building a voting classifier, blending and stacking different models. But my solution is rather simple, just optimizing the classifier on clean data. Thank you for your attention. Now I'm reading the chat. Yeah, that's a lot of code. That is just that is just very, very big. Yeah, I'll share the Google Colab link with you in a minute after I finish my presentation. Yeah, I think everyone just I just went through the values. I just went through the pairs, the objects, and I just knew that something was not right. For example, with some values, and I just looked and thought maybe it should be like the other way, this way. So it has just it is just like an intuition maybe behind the data, because upper blood pressure and lower blood pressure, these values are just, some values are extreme but not really extreme, and some values are just incorrect. And so this is how we are just fixing them. Using Neptuna, it was not critical. It was just faster than using a regular grid search, because I think it is important, for example, when you're using just 1, 2, 3, 4, 5, 6, 7, 8, 8 different hyperparameters, is very, it can be a very long model training if you're using 10-fold cross-validation with grid search, but Neptuna does it much faster, and I just like this library a lot. Yeah. Yeah, I'm sharing the notebook.
Lesha, I have a question. I didn't use pretty much Optuna. I used once, I think, but I don't remember if it's too memory consuming. I know because we have only, for example, in Kyle, we have only 16 gigabyte memory RAM. So I don't know if this, where you run this.
I've run inside my computer. I have 32 gigabytes of RAM, and I have, as I have Linux, I'm using a pretty huge swap file for my work because 32 gigs of RAM is just insufficient sometimes. So the main idea is I have so much RAM, I don't care about it.
Okay. Thank you.
Why I decided to focus just on upper blood pressure and lower blood pressure. It is not the main focus point. It's just the idea that practically nobody spoke about, because everyone noticed that these features have some inconsistent values, but I have fixed them, pretty most of them, I think. So that's why I told you about it. Because I did it. I think that the questions are pretty over. So I will share the notebook link in the Telegram chat. And thank you very much for your attention.
Thanks a lot, Alexey, for presenting and for participation in the bootcamp overall. I guess that is the saddest part of the whole event. Well, before it, I guess I will have to share additional thanks to the participants and everyone who survived through this 2 days, because it was quite intensive. And I'm happy that we have over 75 participants still on Zoom, which is great. And I hope that you utterly enjoyed the whole thing. And I would like also thank all the speakers for their dedication, and particularly Yelena Kantanistova for putting this nice team together. And I also will use this opportunity to probably advertise your master program on machine learning and data-intensive systems. So I guess I will drop a link to her program too on the chat. And what else I would like to say? Tomorrow we open registration to IDAO, International Data Analysis Olympiad. So you're all quite welcome to take part on it. Again, we will advertise everything through the Telegram and additional channels. So hope that this bootcamp will help you to not only to IDAO, but maybe to other Kaggle or outside competitions. I guess I covered everything, and I just want to say like personal thanks again to you all guys for being with us, and keep in touch and have fun. Okay, see you around. Thanks.